the synchronous machine. So under normal operating condition, the relative position of the rotor axis and the resultant magnetic field axis is fixed, and the angle between these two is called as power angle or torque angle. During disturbance, the rotor will decelerate or accelerate with respect to the synchronously rotating field, and therefore relative motion begins between these two. The equation describing this relative motion is known as the swing equation. The stability of the generator will be maintained if the rotor locks back into synchronous speed after having been subjected to disturbance. It is more convenient to represent the J, that is the combined moment of inertia of the prime mover and the generator, neglecting frictional and damping torques from the laws of rotation. So we have J d square theta m by dt square is equal to Ta, that in turn is equal to Tm minus Te. Ta is accelerating torque in Newton meter, Tm is mechanical torque in Newton meter, and T is electrical torque or electromagnetic torque in Newton meter. Theta m is the angular displacement of the rotor with respect to a stationary axis in mechanical radians. The rotor speed relative to synchronous speed is our interest. Therefore, it is more convenient to measure the rotor angular position with respect to a reference axis, which rotates at synchronous speed. Therefore, we define theta m is equal to omega smt plus delta m. So omega sm is the synchronous speed of the machine in mechanical radians per second. Delta m is the angular displacement of the rotor in mechanical radians from the synchronously rotating reference axis. Now the same equation is written here. Now this equation is multiplied on both sides with omega. So the resultant equation, so we have multiplied on either side with omega m. So the angular velocity times the torque is nothing but the power. So we will take the corresponding powers here. Angular velocity times the accelerating torque gives the corresponding accelerating power Pa, and this is omega into Tm. The product provides the mechanical power input minus the electrical power output. So that is nothing but omega m into Te. Now here the product J omega m is called the inertia constant and is denoted by m. Therefore, the resultant equation becomes md square delta m by dt square is equal to Pa, that is in turn is equal to Pm minus Pe. This is known as swing equation with respect to inertia constants. Now let us see the solution of the above equation, that is how to obtain the solution of the swing equation. The solution of the swing equation is obtained by plotting delta versus time t. The resultant graph between delta and t is known as swing curve. So the swing curve is obtained by several methods like point by point method, Euler's method, Runge-Kutta method. However, we will focus on point by point method. In this method, we are interested in observing the change in delta rotor angle during small interval delta t is calculated. So for each small change in time, the delta is calculated and the delta versus time is plotted. Now let us see, before going to that one, this is the graph of accelerating power versus the change in time, that is the time axis we have represented here. Now this is nth interval, n minus 1, n minus 2 interval. So the accelerating power corresponding to nth interval is given by Pa of n minus 1 is given by Pa of n minus 1. Here the accelerating power calculated at the beginning of the interval is constant from the middle of the preceding interval to the interval that is being considered. That is, if you see that one, so this is the middle of the interval, another interval, this is the middle of the another interval. So the accelerating power remains constant here. So that is the thing. Now let us see the delta versus time t. Now nth interval n minus 1. So the change in time between these two intervals is delta t, and the corresponding change in delta is represented by delta delta n. Now from this one, so this is a delta n minus 1 corresponding to n minus 1th interval, and n minus 2 interval, the corresponding angle will be delta n minus 2. Now from this one, the delta at the end of the nth interval, what is the value of delta n? So that is given by, so delta n is equal to, from here to here, delta n minus 1 plus delta delta n, delta n minus 1 plus delta delta n. How to calculate this delta delta n is given by the delta n minus 1 plus delta t square divided by m into accelerating power for the previous interval. So this is what we are going to calculate in this one. So that means our aim is to find out delta for each change in time interval, for a small change in time interval delta t. So find out the delta and plot delta versus time. So the resultant graph will be known as your swing curve. Now let us see, I am going to explain the logic, not the program. So looking into that one, you have to write the program. Now let us take, our aim is to determine delta for various values of time. The same equation which we have derived in the previous slide, I have written it. And how to obtain delta delta n? If you want to evaluate, I am using reverse logic. Delta delta n is determined by using this equation. Now let us see the swing curve. So when you plot a swing curve, so this is how the swing curve looks like. Now here you see this is a time vector, and here this is a delta. So the time vector starts from 0 to the final time, whatever the user defines. Now let us see here, there are 4 instances. That is, one is at t is equal to 0. As time increases, you can see delta continuously increases, and at one point of time the delta decreases. So the point where the delta starts decreasing, so that is known as t clearing time. That means the fault has been cleared, so therefore the delta will start decreasing and becomes stable. Earlier, before t clear, the delta continuously increases, so it will be in unstable. If you won't clear the fault, so it reaches so unstable position. So because at t is equal to t clear is one instant, t is equal to 0 is another instant, and third one will be between 0 and t clear. Understood? So then the fourth interval is between t clear and the final time. Now we see at t is equal to 0, the delta will be different. Between 0 to t clear, the delta will have a continuous values. At t is equal to t clear, so one value will be there. So then it starts decreasing. Now at t is equal to 0, the power is discontinuous, and at t is equal to t clear also, the power is discontinuous. So at these instances, so we have to calculate the average power of the accelerating power we have to consider. Between 0 to t clear, so the power is continuous, that is delta increases continuously. So just you have to calculate the accelerating power. After t clear also, so the power is continuous, so no need to take average power. So you have to consider what is the power during this interval. So this is regarding your swing curve. If fault is not clear, delta continuously increases and the system becomes unstable. So now let us see here, come back after knowing this swing curve. Now this is what we have to evaluate. In order to evaluate this one, so we need to evaluate delta delta n. So if you want to evaluate delta delta n, so you need to know what is the change in delta in the previous interval, that we can define it, initialize it. Delta t square, change in time. So this we have to define it, divided by m, moment of inertia, then accelerating power in the previous interval n minus 1. So how to determine this accelerating power? So let us see. The accelerating power Pa is equal to Pm minus Pe. This is what we are defined. So Pm minus Pe, electrical power output, is defined by Pm sine delta, which is known as power angle equation. Pe is equal to Pm sine delta. However, we have to take the corresponding powers. So that means accelerated power before fault is equal to Pm minus Pm Bf. That means maximum power transferred before fault into sine delta. This is the power angle equation. Now one more instant, before fault, during fault. So accelerating power during fault is equal to the same equation. Only thing is maximum power transfer during a fault is given by, is determined here into sine delta. So then after fault, accelerating power after fault is equal to Pm minus Pm AF after fault sine into delta. So this Pa we are determined here before fault, during fault and after fault. So Pa is there. So this Pa depending on the time instance. Suppose if you are calculating this P at t is equal to 0. So here you have to consider before fault and during fault. That I will be explaining it in detail later. So first, this is how Pa is evaluated. When to take PABF, when to take PADF, when to take PAF, when to take average power. So that I am going to explain it. So now next let us see. Now M we will need to evaluate. So M is equal to, that is moment of inertia is equal to h by 180 into F. That is F is frequency is 50 Hz. So we can evaluate Pa and we can evaluate M. So this is the initialization you can make it to determine. Now you see in this equation PMBF, maximum power transfer before fault. So this equation is evaluated when delta is equal to 90 degrees. So when delta is equal to 90 degrees, so from the power maximum power angle equation, so is equal to EV by X pre. That means maximum power transferred before fault is equal to, this is excitation voltage into the terminal voltage V divided by X pre. That means the reactance, net reactance before fault. Similarly, P max during fault is equal to same E into Y divided by net reactance during fault you have to determine. Then P max after fault is equal to EV by X post. That means the reactance after the fault, that is the net reactance after the fault. So before fault, what is the reactance? During fault, what is the reactance? After the fault, what is the reactances? So we need to know these three values in order to evaluate the maximum power transferred before fault, during fault and after fault. These data are required to evaluate accelerating power. So this X pre, X during and X post must be defined. So here you see X pre, X during, X post will be initialized. The data will be given. So those values will be given. Now in this equation H value also will be given, so that you can initialize it here under reading the input data. So we are going to evaluate this one, we will get this one and we will get all these things. So E and V will be read, and what is the mechanical power input, this one. So we have to initialize it. So these are the input data we need to enter in order to evaluate these things. Now these are the input data which are required. These are the input data which are required for these equations, right? Now let us see, in order to plot this graph, some of the data also we have to initialize. What is the data that we have to initialize? T, time vector we have to initialize. That means we have to define the time whether it is from 0 to 1 or 0 to 2.5. So that you have to define t. Then again you have to clearly specify at what time the fault has been cleared, isn't it? So these details we have to define it. Now for that one, before taking up, so let us take here TF, final time. That means this one will be 0.5, 0 to zero point 0.5. Now we have defined it. So 0.5 means here only. So you are going to get that one. Then what is the change in time? That is delta t. We have to define it, initialize it. That is with a step size of 0.05 till 0.5. That means first value of t will be 0, next value will be 0.05, next value will be 0.1, etc. with a step size of 0.05. Then you have to create a vector t, isn't it? Because delta versus t, so time t must be in the form of vector. So time t vector must be created 0 to 0.5, because final time is 0.5. 0 to, this must be 0.5. It is not 1 here. For explanation purpose I have shown 1. So 0 to 0.5 you have to create with a step size of 0.05. So this is what I have shown. If I am showing 0 colon 0.5 in terms of MATLAB syntax, by default the increment value, that is delta t value, will be a 1 only. So this is what we have defined, and at the same time clearing time we have defined it. Then delta value, that means what is the value of this delta, that is change in delta initially. So the change in delta, that is delta, this one is nothing but your delta. Initially you will treat that one as 0. Under normal condition there is no change in delta, so it will be treated as 0. Now however, you can observe at t is equal to 0, we need to know what is the initial delta, isn't it? Initial delta. So that initial delta 1 is created is equal to d naught into 180 by pi. So this is just a simple conversion into degrees. So how to obtain this delta naught? This is nothing but delta naught is equal to, this is a MATLAB syntax I have written it mathematically. It is sine inverse of Pm by Pm Bf. Pm is mechanical power input divided by maximum power transferred before fault. So this division you have to do it, then take sine inverse. However, here I have shown it in terms of MATLAB syntax. The sine inverse is indicated by a sine. So you will get delta naught, so delta 1. So you got the initial values, all initial values. What is the starting time, what is the ending time, what is the step size, what is clearing time, and what is the initial angle, rotor angle delta, and what is the initial angle of change in delta, what is the change in time. So everything we have defined it. So these are the set of input data we have given it for 1, 2, 3 rows. These are the 3 rows we have defined. From this input data we have evaluated the required data which is required for this one. Is it clear? Now it is clear from this one. You need to evaluate this one for different timings. At t is equal to 0, what is delta? At t is equal to, next step size will be 0.05, what is delta? At t is equal to 0.1, what is delta? Till 0.5 it reaches, so evaluate different values of delta. Finally plot delta versus t. So that will be your swing curve. Is nothing but your solution of the swing equation. Is it clear? So this is a reverse way I have explained it. So what is required? If you want to evaluate, something is required, this one, so we can evaluate it. If you want to evaluate this one, you need to evaluate PA, we have written it, and MA we have to evaluate, we have written. So in order to evaluate this one, we need a P max before fault, during fault, after fault, we have initialized it. Then delta 1 value, initial value we have determined. Then in order to evaluate this one, EV, X-pre, we need exposed, during, we need that we are defined. Apart from the data required for the equations, and if you want to plot a graph, so what are the things, TF, DT, everything we are defined. So these 3 things are your input data. Then all these things you have to write it in the form of MATLAB syntax. So this is what you have to do it. So the entire procedure, that means what, from here to here, from here to here, this one, from here to here. So you have to repeat this repeated calculation at 4 instances. T is equal to 0, T is equal to T clear, and T is less than T clear, this duration, and T is greater than T clear. So less than T clear, power is discontinuous, greater than T clear, the power is discontinuous. So no need to take average power. However, at T is equal to T clear, the power is discontinuous, you have to take average power. Now let us see that one in the next slide, how it is to be done. So this is what I have said it, accelerated power, average power is equal to before fault and during. That means this is the equation corresponding to T is equal to 0. So before fault, and this is during fault. So immediate instant is during fault. So that power average we have to take. Suppose if you take T is equal to T clear, this portion corresponds to your during fault. Then after T clear, this portion corresponds to your after fault. So we have to take during fault, after fault average. So let us see that one in the next slide. Now, how to write the program? There are 4 blocks you should focus. One is at T is equal to 0. Okay, evaluate before fault, PABF. Already all these equations has been explained, and how to obtain this PMBF also explained in the previous slide. The data is ready now. Now at T is equal to 0, actual logic starts. Before fault, then during fault, you find out T is equal to 0, before fault, during fault. Then because as I said the T is equal to 0, power is discontinuous, calculate average power of accelerating power. So average power is this plus this by 2. Now after calculating this one, change in delta you calculate as I have explained in the previous slide. So PA you are going to substitute, M already you are calculated from the given values, delta T also you are defined, change in delta also you initialize to 0 starting value. So all the values are available, so you are going to evaluate the delta and delta N. From this one you find out that delta N is equal to the delta rotor angle in the previous interval plus the change in the rotor angle from this equation. So this is one block. So you have to put a condition in the program. So if T is equal to 0, that means you have to define this time T there. That means one more variable you have to define it in that one. That means if T is equal to 0, then you perform these operations. So for this one more variable which will take care of this timings you have to clearly specify. You are moving from 0 to the final time. So while moving, so you may get a different, you may get a T clear, you may get greater than T clear, less than T clear. Now this is at T is equal to 0. Now at T is equal to T clear, call this as equation 1 and 2. However, in program we are not going to specify. This is only for an explanation purpose I have shown. So when T is equal to T clear, here the fault has been cleared. So once again power is discontinuous. So at this instant, so what is this portion is during fault, and what is this portion after fault. So evaluate accelerating power during fault and after fault. During fault, after fault. Take during fault, after fault. Now take the average of these two will be your accelerating power, PADF plus PAF by 2. So see these 3 steps are same here. Now what we have to do? Evaluate 1 and 2 after this step. So here after getting this one, here I have not shown it. So evaluate delta N for this condition and delta N for this condition. Okay. So in order to see suffix 1, this n minus 1, you need one index variable, and also to have this n also you need one more index variable to access it. So be careful. So while defining in the for loops, all these things will come under for loops because iteratives. So n you need one index variable, n minus 1 you need one index variable to do that one. So that you should take care while writing the program under for loop. So coming back after average power, so evaluate this 1 and 2 in this block. Now the third one, what is the third one? Less than T clear, power will be discontinuous. But less than, this is T clear, less than, if time T is less than T clear, then what is it, this one? Power is continuous. So this portion is known as during fault. So find out accelerating power. There is no need to take average because it is a continuous. So PM minus PM during fault, sin delta. Then coming back to this one, after evaluating PA, that means here we have taken average. However, here it is discontinuous, it is a continuous power. So just PA you calculate it by using this formula. So then evaluate 1 and 2 here. The same formulas, use it here. That means PA directly, whatever you got it, because it is a power is continuous, so you substitute it here. 1 and 2 you evaluate. So this will be your third block. So finally, what we will have fourth block, that means after T clear, again power will be continuous. So therefore here also no need to calculate the average power like how we have done. So just use it like PA, how we have done it, greater than TA clear. Only thing is just use the corresponding maximum power transfer after fault. So which we have evaluated in the previous slide. Now after calculating this PA, again here also evaluate equation 1 and 2. So that is equation 1 and 2. That means this and this you have to evaluate. So now you see you got delta value at t is equal to 0. You evaluated delta for t is equal to t clear, right? Now for less than t clear, so you evaluated delta, that is calculate 1 and 2 I said here. So you are going to get delta values for different values. This will be again under for loop. Each time you have to check whether time is 0 or is equal to t clear. T clear also you have to define it. Or is it less than t clear, or if it is greater than t clear. So it will perform the corresponding instruction set. Is it clear? So this is what the logic 4 blocks you have to focus, and the required data for these 4 blocks already we have calculated in the previous slide. Now after getting deltas for this one, this duration we are getting it here. The delta, different values of delta during this interval we are getting it for this condition. Now after getting this one, just use a plot command in a MATLAB, plot delta versus your time, because time vector already you have defined it. Where you are defined? In the initially, in the input data, you have defined what is the time vector, right? So for each time, what is the delta value you have evaluated from these 4 blocks. So plot delta versus time, so you will get a beautiful curve like this swing curve. So if the fault is not clear, or it will take more time, so delta continuously tends to increase as time increases. That is known as sustained fault condition. So that may also you can check it out by defining a proper clearing time. So it depends on the clearing time. For different clearing times, get the values of delta and plot the swing curve for different clearing time. So this is how the swing equation. So only thing is, first you write this block, second this block, this block, this block. Reverse direction you have to go. Then after performing all these 4, you will get the values of delta and t. So plot delta t. T already you have defined it. Okay. Now what you have to do here to evaluate this one, what we need, how to calculate this one, we have explained it in the previous. So before this one, so you have to calculate all these things, you have to calculate. Also, whenever suffix or prefix is there, so you need to have one index variable to access these variables. That also you have to keep it in mind whenever you are doing writing a program. So any suffix or prefix or postfix are there, you need to have one suffix or index variable you need to have to access that one. So this is regarding your swing curve. So please write the program step by step. Now for first block, you put for loop, if condition, whatever you want here. Because I said when t is equal to 0, it has to perform. If t is equal to 0, it has to perform this one. If t is equal to t clear, this has to perform this one. If t is less than t clear, it has to perform. T is greater than t clear, it has to perform. That means there must be some if condition, or if else chain you can use it. And also in order to access this one, it must be some for loop. And in order to access this t, you have to define some variable where it is going to get a time value, whether it is 0 or t clear or less than clear or greater than clear, you are going to get. Is it clear? So in this one, some of the 1 or 2 variables still we have not defined. So please, now I have explained, you have to define one variable which is going to take care of this t, and also you have to define another index variable in the loops which is going to take care of n and n minus 1. So if you focus on this one, so first a small unit t is equal to 0, you try it and get it, then this one, then this and this. So it should be under for loops and if condition. Only for and if conditions you have to use it to get your solution of swing equation, that is nothing but your swing curve. This is how we are going to get. So once the fault is clear, it becomes stable. I hope you have understood. So start writing the program step by step. So these are the things I have explained it through these references: power system analysis by Hadi Sadat, elements of power system analysis by Stevenson, modern power system analysis by D.P. Kothari Nagarath. So these are the three references. You can refer these books for more theory portions. However, the program wise, so you can write the logic I have explained. So based on that one, you write the program. Okay. So have a good day. Good luck.